So thanks, first of all, for making it possible to give the talk over Zoom. And so I haven't been giving anything, and I was in my previous life participating in philosophy discussions, but I would not say that I have been doing this for a long time. So as I said, Nick, I was trying to gauge the talk in ways that I hope it will be interesting and completely accessible. But if you have any questions which pertains to whether understanding or just in general, please feel free to interrupt. I think that, as I understood, there is plenty of time allocated, so I don't believe it is important that I first give a talk and afterwards there are questions. Of course, I'm happy to stay afterwards for questions, but please interrupt me anytime something is not clear or you would like to ask more questions. So what I will be talking about today is a quite different picture of the universe that you might normally be hearing from physicists. And this relates to questioning the Big Bang and asking, really, from the physicist perspective, if we don't assume that space-time as a whole has undergone quantum gravity phase, which doesn't mean obviously that quantum gravity is not important. I understand, and many of you are interested in quantum gravity for various reasons. So this is not the point of saying, oh, there's no place for quantum gravity in nature, but there is a logical possibility that space-time as a whole didn't explore it. And for what I want to talk really about today is why it's interesting, this possibility, why it's interesting from the cosmology, from the physical cosmology point of view, why this idea that the Big Bang might not have been the beginning opens up new possibilities to explain certain features of the universe that we have been observing the last 50 years. And of course, this will relate to explaining or telling you a little bit about what we know, what we think we know, what I believe all cosmologists agree on, and telling you also a lot about the main concept. So this will be the first, at least the first block of my talk. I want to spend a lot of time on explaining general concepts so that afterwards it really takes only 5 to 10 minutes to tell you why this other picture that I'm pursuing is not at all exotic or difficult to think about, or coming from a really weirdo point of view. Once you see all the basics of cosmology. So, oh, there's already one thing in the chat. Okay, great. So I'll keep
an eye on it, so you don't have to.
Yeah, exactly. So if there are questions, no, I didn't. I just devoted attention to the first chat, but then I leave it to you. Okay, good. So let's just start the first few minutes with simply reviewing what cosmologists talk about when they mean Big Bang cosmology. One thing that they don't talk about is the Big Bang. I don't have to explain it in this round that we don't have a theory of the Big Bang. Even if we imagine it as a beginning, a quantum gravity beginning, there are some ideas, but we just simply don't have a theory that would be similarly well confirmed as let's say, the standard model of particle physics or general relativity in its respective realm of validity. So what we see here is a pictorial picture of the universe that we call the expansion during the past 13 plus billion years. We have both observational theoretical evidence for the fact that we very well understand the universe starting at the latest Big Bang nucleosynthesis. So that's the temperature and time, so to speak, when the first, the lightest elements, helium, hydrogen, and lithium form. And then, is it not? Okay, good. So if we measure in seconds, then it would be the first seconds. Of course, in some sense, this is the worst way of measuring when things happen. And what I mean by 1 second is 1 second after the beginning of expansion. So whatever was the event that triggered the start or beginning of expansion, that's what I call second zero, or the first moment, and then after that, after 1 second, just because we don't know what happened between them. But one also has to appreciate that relative to what would be a quantum gravity energy scale and relative to what would be quantum gravity temperatures, we are already fairly cool. So going from the quantum gravity to nucleosynthesis in temperature is almost as much as going from Big Bang nuclear synthesis to today. So it's a huge temperature jump and huge energy density jump from that we extrapolate backwards. That's not what we do now. We just say that we are fairly confident that starting from, let's say, the first second, general relativity applies on macroscopic processes. Quantum processes are more or less entering only at the perturbative level or at scales that are not relevant to describe the large-scale evolution. So even for cosmology, we will say they are relevant, but they are not relevant to describe the evolution of this large geometry, which at this point, we assume it's already well described to leading order by the field equations of general relativity. And we also know that coming from the very first second, we don't have to change, at least today, we don't believe we have to change the laws of gravity until something happens, namely this decelerated expansion stops and gives way to what we call accelerated expansion. And I will tell more about it, what we really mean by this, even if it's a little bit of repetition to many of you. And then what we believe is, well, given our observations, that the universe starts to expand at an accelerated rate. And this expansion is driven by something that we don't really understand, but we dub it dark energy. So what's the second aspect that's important for this so-called standard lambda CDM? And lambda CDM comes from the fact that, but I will explain in a second, picture of cosmology is that if we assume that the universe, starting second one, the universe is cool enough and big enough that the field equations of relativity govern the evolution, the geometry, given some source, some matter or stress energy source, then what we observe is fairly well matched by what the theory would predict. And this source early on is until around this blob, which we call the microwave background radiation, until the universe cools down enough by expansion that radiation can escape matter. The expansion is radiation dominated. Then it gives way to matter domination. And by matter, I mean really just pressureless matter. Can be baryonic, but it's mostly, we know, dark matter, which we also don't quite know what it is, but what we know is that it doesn't interact electromagnetically. That's everything, or at least our best ideas about dark matter are that. There are some other pictures, but that some fellow theorists pursue, but we don't really believe that right now there is enough evidence to make that as the standard picture. And that goes on for the next over 10 billion years until dark energy a few billion years ago takes over. That we again don't know what it is, but CDM, so lambda CDM stands for cold dark matter, which dominates almost all the evolution that we observe in our past. In the last few billion years, dark energy takes over, and right now, because there is no evidence yet, which would be anyway rather early, but we'll get back to this, that dark energy would be an energy form that also in any form has a time variation. Therefore, we right now phenomenologically often just replace it by something which has an energy density but behaves like a constant and dub it lambda, going back to Einstein, who called it first lambda, and it's the lambda CDM model. So that's about it. And what's good about this picture is that it's very simple on the one hand. On the other hand, it's observationally, so the observations are very rich. The fact that we understand the large scale evolution and are able to check our understanding by observations both of the microwave background and then through observation in the sense of looking by telescope to the sky the last 13 plus billion years, we have a pretty good understanding of that this model is, at least to this phenomenological level, and at least to the extent that we don't believe right now there is any reason to change the laws of gravity during this time, are fairly secure. Now, what is the question? But the question what remains is what set the whole, and this will be really the focus of the largest part of my talk, what gave rise to this picture. And why we know it's not a trivial picture, and at least, from the naive point of view, and everything what I'm saying here, so I know that you think a lot about what are the concepts, what are the proper definition, if it makes sense, as physicists talk, it will probably very often be the case that you think, well, that's not sharp enough, that's naive, what I use, likely, probability, and so on. Please take it in the most pedestrian way of thinking about things. There is nothing behind it that's warrants, so you can ask me about everything, but when I say likely or plausible, I haven't thought a lot about probability measures. So it just means for if you take a flat prior and are naive, then it's unlikely. So, and this is something that I'm sure that you will want to chat later about to what degree it makes sense, because that I encounter still quite often when I informally chat with philosophers that what we in cosmology think is a problem for you, it might not appear to be a problem, but for the purposes of this talk, let me just tell you in what sense we are puzzled by, not just from the fundamental physics point of view. If you come from the fundamental physics point of view, of course, you will ask, sorry, a lot of questions about what might replace, what might unify the two fundamental theories when none of them apply, GR, general relativity, and quantum field theory or quantum mechanics. But if you come from a cosmologist perspective, this question becomes particularly pressing because of what we observe through the cosmic microwave background observations. And what the real problem here is that the universe really, if you don't know the theory of a beginning or a transition to this expansion phase, you really don't know what is a reasonable initial configuration for expansion to start. And by initial configuration, I don't mean here the laws, which laws govern the universe. I said at that point, we believe that leading order space-time is governed by GR, so we go that far, and at small scales or relatively small scales, it's quantum field theory and quantum mechanics. But by initial configuration, we can imagine a lot of different type of geometries in terms of the four metric. And we can also imagine a lot of distribution, a lot of kinds of matter and radiation, or any type of other type of matter. So stress energy distribution around this geometry, even consistent with GR. As a matter of fact, this is how the discussion started in the 70s, and people started to extrapolate backwards in time. It turned out that if you just take general relativity, and even if you take some sort of geometry that is already fairly smooth, meaning that it's almost homogeneous, so it almost doesn't matter where you are and in which way you look an isotropic, just to have in that geometry no spatial curvature. So by spatial curvature, we also mean, again, if triangles are closing at 180 angle, no, that's the simplest. So are we Euclidean or are we something else? And the answer was, by this naive flat prior measure over the set of initial conditions, that most initial conditions would not give us the microwave background, and they would not give us the microwave background in different ways. Now, in what ways? First of all, just to go back and say how we think about it and why we, when I say in different ways, well, most thinking back then was, what if we start with a Big Bang? And that's what I will assume first, but I again just wanted to, really emphasize how that thinking is really fuzzy, because as Jim Peebles would say, who is by many measures one of the real fathers of physical cosmology, said we just don't know. And it's unfortunate that we think of the event that set the initial data as a Big Bang. But this is what happened. And so I will use the Big Bang in this talk whenever I forget about it, that I shouldn't use it. But especially when we set the initial conditions, people were thinking about it. Okay, let's imagine there was some sort of Big Bang, some sort of quantum gravity beginning, and it gave us some sort of distribution of initial geometry and initial conditions. What can we read off from the microwave background about these initial conditions? So around the 1 second mark or earlier, a fraction of the 1 second mark. And what we can read off is this: it's boring, but it's scary boring. In a sense, scary boring that the initial geometry was maximally symmetric. So the microwave background, the temperature of the microwave background fits a perfect black body spectrum, which means that whenever it was emitted, and it was around 400,000 years into the expansion phase, which cosmologists, I know it sounds like a lot, but we nevertheless call it a baby picture of the universe, just given the fact that 400,000 years are still very little compared to 13.9 billion, 13.8 billion years. And the scariness, so why it's scary that the initial state with respect to both the geometry and the distribution of energy density is so uniform, manifests itself in different ways. First of all, first from the naive understanding, why should it be? If there was some sort of Big Bang event, why should it give us such a simple universe? But second, and that's what many has learned to call it, the horizon problem. If you look at this, and horizon is a fuzzy word, really. In cosmology, it can mean a lot of things. Some people think of it as a causal horizon. Some people think of it as particle horizon. It's not so important. I try to avoid using the word horizon, but really what most cosmologists mean by the horizon is it is the maximum distance at which interactions, physical causal interactions, local interactions can take place. And the fact, of course, we know why this comes from, where this comes from, that there are that there is a limit as to how far you can see, as to how far you can send a signal within relativity is, of course, the fact that the speed of light, so general relativity is fundamental local theory. That means that information can propagate only at a maximum speed, and therefore we can, using just this fact and knowing the propagation, maximum propagation velocity of any type of information, we can calculate what is the maximum blob, what is the maximum patch within the micro background radiation within the universe at 400,000 years or today that could have interacted, and where the scariness comes from. And this is, I believe, what massively made the discussion so urgent about the Big Bang initial conditions, is that what you see here is around 10 to the 28 or 10 to the 29 disconnected regions in the early universe. And so whatever homogenized and isotropized the geometry and therefore the distribution of the energy densities, matter, radiation, whatever is there, was a process that by simple general relativity source, where the evolution is sorted by simple matter or radiation, would lead to a process where really 10 to the 29, that's a huge number. I mean, I have troubles imagining it. Different regions of space-time had to be tuned together by some physics that we don't know. And so that was really I believe in the late 70s, the reason why people started to think about considering the problem as a problem. Now, thinking has been changing since then as to what degree this is a problem. But even if, and there are a lot of colleagues who say we may or may not be able to explain the background geometry. So by background geometry, I mean this uniform, homogeneous, and isotropic Friedman, Roberts, and Walker spacetime. But there is a second problem that we absolutely must explain. So it is not just that there is this so-called horizon problem and the smoothness and flatness problem of the background geometry. There's a second fact we know about the microwave background. So it's the same problem also appears as a so-called inhomogeneity problem in the early universe, because one can ask now, okay, to leading order, and that's what people measured first, the microwave background is as homogeneous and smooth as you can get. So then the next question what scientists would ask is, what can we measure? Well, how deep do we have to go in order to find deviations from this absolute homogeneity? And the temperature distribution, which manifests deviations from this maximally symmetric initial space-time geometry and maximally uniform distribution of matter and radiation. And the answer is, again, scary. It is, you have to go 5 orders of magnitude to 5 variations. So this map that you often see as that people, especially astronomers, call the baby picture of our universe. This is a deceiving picture because it would look to you as if the picture was manifesting a universe that is, not that homogeneous, not that isotropic. There are blue regions which represent regions that are colder than the mean, and a lot of hot regions that represent regions that are a little warmer than the mean. And if you look at it, you would not be able to immediately read up the statistics. So if I tell you that actually it doesn't really matter where you are and where you look at this map, And you will always see the same average deviation, namely the delta rho, so the deviation, or delta t over t normalized deviation is 10 to the minus 5. So 5 orders of magnitude magnification of the original map. Then you would not be able to say, well, you would just not be able to see that. But I have to tell you, this is what we measure. No matter at what length scale you look, no matter how big the patch that you take, you will always find that the average deviation is 10 to the minus 5, which meaning that no matter, how big the blurb, you can take a small blurb, you can take a Blipberg, the statistics will always tell you the average deviation from the mean temperature of 2.7 Kelvin is really 10 to the minus 5. And that's incredible tiny, and that's what people call scale invariant. So that whatever there was that said this initial homogeneous geometry over 10 to the 28 or 10 to the 29 patches that also arranged for the deviation from this average energy density and from the average geometry to be incredibly uniform. So the deviations are tiny and what we call scale invariant. So no matter how you zoom in, what sample you take, you always get the same answer. It's 10 to the minus 5. And if you ask what is the statistics of the deviations, it looks like that our universe just wants to go simple. It turns out it's Gaussian. So if anybody asks, what kind of statistical distribution can you think of? I think most of us would name Gaussian because that's what we learn already in school. And sorry. But it turns out to be, we don't see any evidence from deviation from Gaussianity. So we call it, in this sense, these fluctuations simple. And now where the scariness comes from, not that it's just synchronized, you can again, over this 10 to the 29 causal disconnected regions, the problem is according to relativity. The problem is that even if you take just one patch where it and ask, what are the deviation within one patch, even little perturbations extend, what we call little in this map, extend over regions that are disconnected in terms of, we don't believe that within GR, using GR and some ordinary matter radiation source, there could have been local interaction between these patches. So this is, so to speak, our understanding of the problem of the microwave background. And admittedly, most of my colleagues, I would say today would say that the real achievement of early universe cosmology is that we have some scheme to understand the fluctuations. And I think a lot of my colleagues, and I would also say, would tell you that they don't really care so much about the initial conditions problem. And I would say, I think it's a very important problem because in order to explain the scheme that we have, to explaining the perturbations, of course, heavy rest on the fact that we can explain the initial homogeneous geometry. So this is a little bit of an understanding what is the weight that we assign this problem. But what we know is this map is not just the one takeaway from this, first intro 20 minutes would be that from the cosmologist point of view, this is a problem because of this local interaction not being possible, but nevertheless we observe something at back those time over these scales. We observe something that seems to be in some sense communicating, in some sense extremely well synchronized. And now, if you ask, so the lore was okay. How did we get to the standard explanation that I will explain a little bit in a second? Well, the lore was, maybe we will never have. So this is the cosmologist perspective. It is not the fundamental physicist perspective. They would never say we can never get to the theory of quantum gravity. But a cosmologist asked back in the early 80s, and that's what eventually led to Guth's paper on inflation, was, well, however the universe comes out the quantum Big Bang, it looks like very special. But how about can we perhaps write down a theory that is insensitive to the state that quantum gravity gives us, if we assume that the universe began in a bang, which is just a placeholder for some quantum gravity event? And I think the answer today is that we know, even if we go, and I will tell you about that in a second, with the standard explanation of inflation, we are not even inflation, in order to start, it's not insensitive to the quantum gravity phase. That, of course, brings back both quantum gravity or possible alternatives to it for the beginning of the universe. to cosmology too. So what we have learned during the past, I would say 20 years perhaps, but at the very least the last 10 years, inflation itself is sensitive to initial conditions. However, what one way of saying is why the quantum gravity event is definitely a problem and definitely required some explanation how it got to universes, or is that when you look at, there is one way, and this way we owe to Penrose, and he was extremely sharp about pointing out this problem already in the 80s, 86, who said that one way of looking at this, what I explained you, so that I explained you the cosmology standard way of expressing the initial conditions problem. By quantum gravity beginning is a problem for what we see in a microwave background has a different face. And this different face is something that Penrose called the cosmological entropy problem. Now, this entropy has really nothing to do with the thermodynamical entropy. We will get back to that too, because once I talk about balances, I know that is a question that everybody has on their mind. But this entropy problem that Penrose been emphasizing is a different one. It's a cosmological entropy problem, which points out that, and here really entropy is a very simple concept in the sense that what Penrose means by it is really just the gravitational degrees of freedom that are being excited. And entropy is a measure of it. So large entropy would mean a lot of gravitational degrees of freedom are excited. Tiny gravitational entropy, as we measure it, very few gravitational degrees of freedom are excited. And you should not be so surprised when I say in the early universe, the entropy is tiny, because in order for it not to be tiny, you would have to see such a space-time. So exciting degrees of freedom means that lots of degrees of freedom in the metric would be excited. That would not lead to a maximal symmetric initial configuration, where all the gravitational degrees, gravitational wave degrees, the vector degrees, and nearly all scalar, except for one, scalar degrees of freedom are just frozen out, already not excited. And that was, and moreover, when we go over to the thermodynamical question, even the distribution of the energy density, that's also very smooth. So it's tiny entropy, but Penrose wanting to point out, coming out of a Big Bang, one way of interpreting and this will be important later. That's why I'm mentioning it. And also I'm mentioning it because many don't mention it, but I think that given that Penrose now got the Nobel and goes around talking about it, it's not just for that reason time that you might be hearing it too. So it's good to order it in how it relates to the usual thing that cosmologists talk about. So the entropy problem is pressing for a quantum Big Bang, because now you would expect that quantum physics does excite all degrees of freedom, and now you have to explain it when it goes down and classicalizes. How is it possible that almost no gravitational degrees of freedom are excited, and the entropy is partitioned in a way that almost all entropy is stored in the matter radiation sector, but almost no entropy is stored in the gravitational sector. So the cosmological entropy problem, according to Penrose, really has two sides. The partitioning of the entropy. Why is there almost no entropy stored coming out of the quantum Big Bang in the gravitational sector? That's the partitioning problem. And why the second problem is the total entropy. Why is the total entropy tiny? And just for completeness, as a matter of fact, Penrose is pursuing, even though he was the one who with Hawking wrote down the singularity theorems, where many people think that means that there is a Big Bang, he himself says he sees the cosmological entropy problem to be the main reason why you might have to give up the idea of a quantum gravity beginning for the universe. This is just on the side, and we can get back to this. Good. So just 5 minutes on the standard picture. So what people thought is inflation never focused on this problem. As a matter of fact, the standard entropy problem that inflation is unable to solve, the standard entropy problem was pointed out by Penrose after inflation was discovered. So this is already something that if you care about this problem, what I will tell you won't be that interesting. On the other hand, inflation is the standard theory that most of my colleagues pursue and believe to be true one way or the other. Therefore, it belongs to a cosmology to talk about it and present it to you. So the idea was the same what I mentioned is, forget about the entropy problem. Inflation cannot solve that, could never solve it. But can one write down a theory that leads to initial conditions irrespective of as to how you come out of the Big Bang, that produces the microwave background as we observe it, namely a large-scale universe that is maximally symmetric with respect to its geometry, and in which the matter and radiation is distributed in a most uniform possible way with little deviation following an extremely elegant scale invariant and Gaussian distribution. And so Good's idea was back in 81 to say, perhaps there were some patches that were already fairly homogeneous and isotropic, rare patches, that doesn't matter how rare, coming out of the bang, but those patches were filled with something that we call a scalar field. So it's not matter, not radiation, but something. We know that those fields exist. Higgs field was just detected less than a decade ago. So a field that permeating all space-time and has some strength. We can assign to the field a strength in every space-time point that permeated, and we usually characterize such fields by their kinetic energy and their potential energy density. And such a field dominated patches, some rare patches, and led to a phase where those patches expand at an accelerated rate. Now here it's really important, and I said that I would get back to what we mean by accelerated expansion, because I believe that you will, once one defines it properly, you will also understand why this was such a natural thought to bring in to solve the problem of causal connectedness. But the fact that I have been so far only talking about, even though I mentioned a lot of relativity, there was nothing genuinely relativistic except for the finite interaction speed or the locality of the gravitational theory that I brought into the discussion. But there is a second aspect that makes our universe very relativistic, namely, how do things evolve? How does the scale of interactions, of local interactions, of the scale as far how we can see, versus at what rate physical distances move apart due to the dynamics of space-time behave? So I see I get a lot of chat questions. Is there?
Well, Chris is having trouble with his audio, I think.
Okay. Oh, okay. Sorry, then it's nothing. I just
okay,
good.
Just go
good. So
on.
Okay. Sorry. So the important thing is here that there are two scales that we have to consider. Decelerated expansion means that let's start with that. That we know that, and that's what I said, there is one factor. So Friedman-Robertson-Walker, a maximal symmetric spacetime, it's really described by only a single dynamical parameter. That's what we call the scale factor. And the scale factor really just measured at what rate during an expanding universe physical distances grow. So at what rate galaxies move away from one another, at what rate planets move away from one another, and so on. Black holes move away from one another in space-time. But there is a second distance in relativity, and that's what some people call sloppily horizon. I prefer to call it the Hubble radius. That is the distance, that's the unit distance of causal interactions. And the interesting thing about relativity is that these two distances don't evolve at the same rate. Decelerating expansion, what happens is decelerating because physical distances expand slower than the Hubble radius. And so stuff comes into our field of sight that was outside of the unit causal interaction pattern. Now you might understand what we mean by this what we call causal horizon or Hubble horizon problem, that it takes a decelerated universe to see stuff today that wasn't in our, you can call it past light cone, or in our causal horizon. And during accelerated expansion, the opposite happens. The scale of physical distances expands faster than the scale of interactions. So what happens is, and this is what's happening today too, that's what we call dark energy expansion, stuff is going out of our Hubble patch or Hubble radius. So what we see becomes inaccessible to us. We cannot see as physical distances expand. So as you can see it, what really was happening since the first second, stuff was flying into our Hubble patch due to the fact that physical distances, if a universe is in a relativistic universe is dominated by matter or radiation, then stuff is flying into our Hubble patch. So that's the reason why we can, in the microwave background, see many exponentially many patches from the early universe that were inaccessible to a local observer back then. And when decelerated expansion gives way, when the dominant energy density content changes, so that the driver, so what the rate is determined by is your energy content, and so dark energy changes that and makes things go out of our Hubble patch. Now, if I think if inflation hadn't been discovered in the 80s, probably people would have brought it into the discussion after dark energy was discovered, only for the reason that classically, this gives us, obviously there exists a form of energy density. We don't know what it is, what we measure, it's a fact on space-time, that leads to an evolution where things fly out of our Hubble radius. And this is exactly what you would need in the early universe if your chief focus is to explain why you observe in the microwave background features that locally, if the universe has always been decelerating, couldn't have been an interaction. And that is really the idea of inflation, and chats come in, to introduce a phase within which exactly this happened, within which the Hubble patch was nearly constant. That's why some people call it the sitter-like expansion among those who might be familiar with this, and I know that there are a lot of experts who probably are familiar with this phrase, so that the scale of interactions remains nearly the same. But what happens is physical distances expand at an accelerated rate, so you exponentially multiply the feature. You can extend the features of, even if it's a rare patch, so you can just need the right kind of a patch. It can be very rare. That was the idea. The idea was it's reasonable to assume that there are rare patches, even after a quantum beginning, that can give rise to a phase of accelerated expansion. These rare patches already have the almost right features, almost homogeneous, almost isotropic. And by the phase of accelerated expansion, the features of this one patch get extended over exponentially many patches. And these exponentially many patches build then the initial state for decelerated expansion. And so that's for the background. And for the perturbations, the idea was that the same happens to the fluctuations. Any type of fluctuations, even fluctuations in the energy density in the scalar field energy density that drives the accelerated expansion phase. We know matter or radiation cannot drive this phase, but a scalar field can drive this phase, and tiny little quantum fluctuations in such a field would also extend over exponentially many Hubble patches, and these would be the fluctuations that we today see in the microwave background. So this idea is so simple and that's why I believe was appealing. And a lot of things, you can fit to this idea in ways that you can. So physicists are clever, and you can write down all kinds of scalar field potentials that then eventually give you the spectrum that you measure. Now, there are many ways one can go from here. And because I think you invited me to talk about what I'm working on, I would say if you are interested, later ask me questions about, why would one not accept inflation apart from the entropy problem? Why would one work on other issues? But might be that many of you already read about it and you couldn't care less, but let's just say that I personally, since I was a grad student, have been bothered by a few issues with inflation. And again, please ask me if you care later, but I think it's more interesting to tell you about the physics I'm working on. And some people, and one of the issues I have been troubled by is initial conditions problem. Some people, other issues that have been pointed out for a long time, eternal inflation. It's another problem that I have been troubled by. Nevertheless, the question arises, okay, by Penrose, we know. So if you are not troubled by many of the issues that I mentioned, whether inflation resolves the initial conditions problem, whether there is a problem that inflation is eternal, you still should be worried about something that people didn't even know was a problem. But if you assume a quantum beginning, inflation is unable, because it never was designed to explain this problem what I mentioned. So I don't want to repeat it. Both why is the initial entropy low, and more importantly, why is it stored? Now it's bad. Now there is one thing what inflation made worse. So inflation cannot add anything to explaining the low entropy, but it's one other thing that it made worse. So earlier, when you just assume simple Big Bang cosmology, so some sort of quantum beginning that gives us exactly the state that due to decelerated expansion leads to a microwave background, then at least you could assume that just the gravitational sector was unexcited. Just the gravitational degrees of freedom were all frozen, and most of the entropy was frozen in the matter radiation sector. But now what inflation requires, that all entropy is homogeneously distributed in the scalar field sector, and the entropy is also tiny in the matter radiation sector. So now you have to explain that in addition. And maybe this is the point where I should just mention one thing, because just as many of us often forgets mentioning it, there is nothing wrong with Big Bang cosmology. So you don't need inflation because there is an inconsistency. So we don't have the laws, or we find something why the laws don't apply that we know describe the evolution, at least in the microwave background. It's really in the sense, and it's a very peculiar problem for physicists because they never have to otherwise encounter, is that we actually have the laws, we have the evolution equations, but what we discover is, well, this is the one point where it is strange that the initial configuration, usually you just consider it as an input and we don't bother with them. But in this case, the initial conditions, if you don't assume them, and some call it finely tuned, I don't know if it's a proper word of saying it, but if you don't assume them in an exact way as it's needed to observe what you measure, and this is it is like ultra exact what you need along the lines as I explained, then you don't get given the same laws what you observe. So in this sense, the Big Bang cosmological model is not wrong. It's not inconsistent. In this sense, it's more like in this sense that we say it has an initial conditions problem. That's what inflation was trying to solve, but instead of solving it in a certain sense, it pushes it further back. Now you ask it how to stop inflation. Also, how natural or how satisfying are the conditions that you need instead for inflation to start. And for that, Penrose said this is, and this is in this context, that's why I'm mentioning it, that Penrose says this is very dissatisfying. So he quantified, and we can talk about it. I'm not perhaps the best person to say by what measure it's less likely, more likely, but Penrose would just say that actually it's easier to get Big Bang cosmology without inflation as you observe it than with inflation. And so that was the reason, and so I have around 15 more minutes at least for the talk, and that's probably more than enough, that some people started to think already in the late 90s, early 2000, when I myself was in high school. So unfortunately, I cannot credit myself with this, even though it's a great idea. To think about that perhaps one of our assumptions is wrong. So if we really consider as cosmologists the initial conditions problem a problem, not just something that, okay, we can just live with, we just put in the conditions that we measure and run the simulation, then it might be that something has to give. And, one obvious elephant in the room is that might have to give us this idea that there was a beginning. I mean, an absolute beginning. And there might have been even an absolute beginning, or at least our decelerated expansion phase, whatever gave rise to it was the absolute beginning. I prefer actually the second consideration. So, the big question whether, and we will get to this, whether there has been at any time an absolute beginning from which spacetime emerged, I think is somewhat different from the fact what is the best explanation for the initial conditions of a decelerated phase. And there you might think, well, it might not have been a quantum gravity phase. Maybe it's something else. And let me just turn around the argument and show you why it is attractive from the cosmology point of view. If you want to solve the type of initial conditions problem that I've been presenting to you that leads to the microwave background, if you don't assume that the bang was a beginning, but assume that before decelerated expansion started, there was a phase within which the universe contracted now contract then to a certain size, and this end by it contracted, heated up, and this hot small Hubble patch transited through a bounce, which is now replacing the bang, to the decelerating expansion phase. And since I know the people who started, it was Steinhardt, Turok, and other collaborators who started working on it, I know that the main reason why they found this idea appealing is exactly the way, this contracting phase might solve the problem of how do you get a beautiful, simple background geometry, and how do you get fluctuations around it that are exactly scalar and non-Gaussian. And this all goes back, and that's why I was stressing it. It should be not simplified a good job, because it all goes back to the fact, to the fact that we live in a relativistic universe, and assuming some sort of a particle or matter content will define the relation or the rate at which physical distances, in this case, contract versus the Hubble radius contracts. And a scalar field, given its potential, can trigger accelerated expansion, but in a contracting universe, it can also trigger slow contraction. And what is slow contraction? Well, slow contraction is a phase, and this is the only notation that I'm introducing. So where h is the Hubble h 1 over h is the Hubble radius, because h is the Hubble parameter, and a is just a scale factor, and t is some cosmic time, t not some initial time. And you will see here, you can read off everything: matter domination, accelerated expansion, decelerated expansion, contraction. If the universe contracts, a shrinks. So h is negative because h is measures the velocity at which, or the rate at which a shrinks. But its absolute value, so h is becoming more and more negative, its absolute value grows. Now, why is it important? Because h itself, so its inverse, is the Hubble radius. It measures the unit of causal interaction, or the maximum distance as far we can see. But it also plays another role. The Hubble parameter square itself measures total energy density. So you can read off a lot of things from this little relation. And epsilon tells you it is a feature of the dominant energy density. So what happens here is the dominant energy density tells you at what rate the Hubble radius contracts, or in an expanding universe would expand. So this relation is valid for both, while A contracts as a function of A. So for example, in a, let's just so it is familiar to you, in a decelerated universe where things come into your horizon, the important thing is that epsilon is greater than 1. So the Hubble radius is expanding faster than your physical distances. That tells you that your patch the Hubble patch becomes bigger and bigger relative to the physical patch, which is our universe. So you see, or initial universe, so you see more and more stuff that you couldn't see initially. And an accelerating universe, epsilon is smaller than 1. So h hardly moves anything, the Hubble radius hardly moves anything, but stuff can fly out of your horizon. And it's important on a Hubble radius. Now, slow contraction is the opposite idea. How about we just shrink in on our physical patch? So that's slow contraction at physical distances. So two black holes hardly move, hardly get closer to one another, or two galaxies hardly get closer to one another. But what happens instead, the Hubble radius, the Hubble patch shrinks in on so it shrinks much faster. So epsilon is typically a big number, shrinks much faster than the Hubble radius, than the scale factor. And so just for those of you who want to know, it's really epsilon is the idealistic approximation of it is that if you have a homogeneous isotropic universe, then any form of matter density behaves as if it was a perfect fluid. So you can characterize it just by its pressure, its energy density. So it really tells you, I just want to show you that it's really manifest that the beautiful dynamics of the geometry is entirely determined by its energy content. And so you can see the slow contraction requires something that's very high pressure, and accelerated expansion requires the epsilon should be greater than 3. And accelerated expansion requires something, and now we'll have to watch, which is negative pressure. right? Because epsilon has to be smaller than 1. So so some of you might know this ratio as W. So through cosmological constant accelerated expansion is P over rho is -1. So epsilon is actually 0. That would be what some call the Sitter expansion. And that would mean if the dark energy is a true cosmological constant, that would be, just so connect some other knowledge, this would be then negative pressure, and for slow contractions you need high pressure. And what happens here is, again, for the expert just or those who want to know more, you take some sort of negative exponential potential, and what happens is you have a scalar field that is going downhill its steep negative exponential potential, triggering the universe to extend the features of one Hubble patch. So remember, in inflation, the idea was to extend the features of one rare Hubble patch over exponential many Hubble patches by keeping the Hubble radius nearly constant. Now, slow contraction is the sister idea, and it's telling you what you really can do during a contracting phase, do the opposite, extend the features of one huge patch over exponential many Hubble radii by shrinking in the Hubble radius on, this is just details, so let me just skip that, on the universe. Now, this is something that I just want to mention, because these are the type of things I'm working on. What we have been doing on, and because it's really neat, it uses the same feature, same technologies, just adapted to the case of a contracting universe as colleagues use who model colliding black holes. Of course, you might ask, and I believe that a lot of you ask, since it's conceptually, obviously, there is something that both inflation and slow contraction, so far as I explained, you assume. Now, how on earth do we solve the initial conditions problem if the inflation explicitly assumes a rare patch that already almost has the right features and focuses on extending the features on super Hubble scales? But what I was presenting you was the same for slow contraction. And what one can do is one can push the idea and ask, well, how about taking a scalar field? And this is one of the second to last slide, so I'm almost done. How about taking a scalar field and giving it a negative potential, but now using the fact that we have very powerful computers, and you don't really need even that powerful computers, you rather need powerful thinking about how to code up the Einstein equations over on the computer and solve them for general metric configurations. And what I have been, busy with the past few years is doing this for contracting universe and asking, okay, in a contracting universe, at least when you start contracting, you are definitely leading order classical. So you don't have to worry about leading order quantum effects. So you can ask us, what is the initial configuration? And, it's a different question where it comes from. How generic the initial configuration, metric and matter configuration can be, scalar field, matter radiation, and so on, curvature, spatial curvature, shear, that you still get to a smooth and flat universe. And it would take a lot to explain. Just let me explain you a little bit about what we do here. So what we do in the simulations, we put the universe into a box, and it's a periodic box. So essentially the universe has no, very different from black hole simulations where you have you put a black hole into a box that has boundary conditions which are flat. We have periodic boundary conditions, which means you could put a lot in the sense you see a lot of universes next to one another. So you have periodic boundary conditions, a replacement for having essentially as good as no boundary conditions. So you have a universe in the box, and you run the Einstein equations about this universe, you have some initial metric and matter configuration. That's what you see here. And then you can ask a lot of questions. So you can, once you solve the Einstein equation and therefore nonlinearity, you can ask all kinds of questions. You can, for example, how do the normalized energy densities behave, or shear densities, curvature densities? And in some sense, it's a very simple manifestation of the powerful or a power of smoothing to slow contraction, because what you want to see here is, so I just quickly will run it for you in a second. It's very quick. What you will see here is a universe in a box initially dominated by shear, which is anisotropy. Very inhomogeneous shear. You could never approximate it with those little equations I was talking about. You also can see here lots of spatial curvature with red, and this initial vacuum energy scalar field energy distribution. Now, sometimes we add additional matter and radiation variation. They would be, some behave like shear. So radiation behaves very similar to shear, and matter behaves very similar to curvature, exerts a lot of gradients. And so what you want to see is, I call the simulation probably the world's most boring simulation, for which you need over a year. That what you want to see is, at the end of the day, blue dominates, and blue is uniform, no matter how you start. And working with lots of postdoc and students, we ran thousands of simulations, and this is something generic you will see, and this will be quick. This is really quick. What measures it is the number of efforts, so e to the something by how much the Hubble radius involved. And so what you see here is, it's incredibly quick how this scalar field, which initial distribution can be very different from homogeneous and isotropic. So it's very different from the cartoon picture that I had showed you, and very different from the initial configuration that's necessary for inflation, leads to a phase that is going to flat and smooth universe that's ready to bounce, so to speak. And just so you see, if you slow down the simulation by 25 times, it's quite pretty. It's a very nonlinear process, lots of details to it. Ask me if you care later. But the point is that it goes very quickly, and it's very robust to initial conditions. So we have here a theory, at least from the physics point of view, that really doesn't care what the classical initial configurations are, which is very attractive. So, and I would say that this is the best part of the story. That's what I'm most excited about, that we have under full control a theory that only requires general relativity with a scalar field, and is insensitive to initial data, and gives you a geometry of space-time geometry as ours. Now, of course, you still contract. So what you really want is, you have to transit to an expanding universe. But this would be the picture. So the picture would be that you solve the initial conditions problem during this slow contraction phase, which is insensitive to whatever your classical initial configuration was. So this is a one-time event. Give me a last slide, and I will tell you a little bit about it, what we think, what comes before, if it's a problem or not. So it could be that it's infinitely far in the past. It's a geodesically complete model, and you don't have to ask any more initial conditions question. It's not very satisfying, but for a one-time event, to explain this guy, this would be enough. And the second problem is we are working on is, we want to transmit this stage to start decelerated expansion. So here, there is no inflation. This is all decelerated expansion, and two are connected by a bounce. And now you could still ask one question, and we will get to that. And this is what I want to close with. So first of all, did you solve the entropy problem? Did you solve the gravitational entropy problem? And how do you avoid this odd entropy problem that everybody raises his or her hand when anybody starts to talk about bounces? And that's what I want to close with. So I wanted to give you the motivation why, it's very similar to the idea of inflation without, and that I didn't talk about, so please ask, without encountering some issues that inflation does. The initial condition problem I was talking about, there is this eternal inflation multiverse problem. It doesn't encounter it. But a second question is, and that has been one of the focuses, a problem that inflation has never been addressing. Can it solve the entropy problem? And a problem, oops, I'm closing in 2 or 3 minutes.
Sorry.
No worries, I'm almost done. That since Friedman first proposed an oscillating or a bouncing universe was answered, the thermodynamic entropy problem, how can it be addressed? And what will be important for the last 3 minutes of my talk is this: how we imagine the bounds, how we are trying to model it. So you could ask, what is different? Why? Okay, this contracting phase is fine. Excuse me. This contracting phase is fine, but what do you do about the bounds? And that's what Tolman was already asking Friedman. What do you do about these bands? Because there are multiple problems if you start to bounce in the way Friedman wanted to bounce. So, and these problems that were pointed out by Tolman can have 3 phases. And all relate to the fact how you bounce, except for the second one. So I was not talking about one issue, and let me start with the chaotic mix master. So for a long time, and this was even actually mentioned in Kip Thorne's thesis, people thought that you cannot beat anisotropy in a contracting universe. This was really up until a few years ago, and I believe we really showed it first that it's possible with our simulations. Lately, the so-called mixed master behavior that comes about due to the fact that people thought you cannot beat the shear. And this is a little bit historical, and I believe it might be interesting to you also from a historical philosophical perspective. This was the idea relativists thought a lot about what are reasonable forms of matter and radiation. And very often this was thought about in terms of perfect fluids. So very often people thought about it, well, what are reasonable forms of matter or radiation that can be characterized as a source of perfect fluid, which very often is just coming down, what kind of relation between the pressure and energy density can be assumed. And I was a little bit swallowing it because I didn't want to become too technical, but if the only type of matter that you are ready to, so if you exclude scalar fields, the anisotropy really cannot be beaten in a contracting universe because it would need a perfect fluid that has ultra high pressure, which leads to superluminal propagation. So perfect fluids cannot have a pressure greater than P over rho cannot be greater than 1, because that would mean that their sound speed, so the speed of propagation of the modes, are superluminal. However, for scalar field, this relation is not true. The ratio between scalar field energy density and pressure is unrelated to its evolution equation, where the propagation speed of mode is always 1. So the big, so the reason why there is no issue with beating the shear is because we consider scalar fields in modern cosmology, and there are high pressure scalar only requires a negative potential energy density, which is sufficiently steep, and that propagates the modes of which propagate with CS with the sound speed 1. So just as any type of reasonable matter radiation will propagate, so not exerting superluminal behavior. And this would not have been possible at the old point of view when GR people were only considering perfect fluids. So that's easy, but it's unrelated to the bounds. What's related to the bounds is higher bounds. So Friedman was proposing that, so in order to bounce, you have to transmit from a contracting phase where H is negative and growing. So the Hubble radius is shrinking, but is negative, A dot is negative, so the scale factor is shrinking, to a phase where the Hubble radius is positive and big, and A is growing. And as Friedman, so what you really need is necessary condition is that you change the monotony behavior of the Hubble radius, going from shrinking to growing. But so this, you would think that the black curves represent the Hubble radius, but in Friedman's model, they represented the scale factor. And it's indeed true that as long as you crunch, as long as you not just make the Hubble radius shrink and then grow and shrink and then grow, but also the scale factor, so all physical distances, you cannot, I don't believe you can solve that problem. That has been already pointed out by Tolman. Because of these two facts, if you bounce only at the quantum gravity regime, you cannot pretend black holes getting infinitely close together, and therefore, because they store all entropy at that point. And by the way, the matter and radiation won't help you either, but they will just build up infinite entropy, and you necessarily have to crunch, whatever that is. And so even if you get out of that phase and start decelerated expansion through inflation or without, that won't give you anything, then you haven't solved through the slow contraction phase or to balance any of the problems. So cosmological, why it's possible, it's cosmologically uninteresting, and it suffers from these two problems, that you not really have just the same bad entropy problem if you have a one-time bounce as the Big Bang cosmology. But if you have a cyclic universe, it's impossible, since you keep reaching infinite entropy, so you should be stuck there, but you propose that you get out of that. So this was the old Friedman problem. And so what we have been proposing as well, the idea that the scale factor also oscillates is just not necessary. I just wanted to show you how, without a scalar field, so this is just a neat feature. So if one numerically models a universe where there is no scalar field with a negative potential, but just matter and radiation, then the energy densities lead to something which is a true chaos. So it's really just pictorially, it's not so important what it means, it's total chaos. And this is a mixed master chaos. We now today can actually confirm that with simulations. But if you, this is what I want to close with, if you assume that only the Hubble radius oscillates, and you don't, and this is why it's important. So you say you could ask, so I don't think it's impossible, it's an important scientific question to ask, if there was a quantum Big Bang or a quantum bounce. But if you want to solve the initial conditions problem in the sense as I was presenting it to you, through the slow contraction phase, without encountering the Tolman entropy problem and the crunch and having to start again because you're going to excite all degrees of freedom to this quantum gravity phase, short of an explanation why it doesn't do that. It doesn't give you anything. And what you have to propose is it's a logical necessity, so to speak, and then afterwards, I think in this context, and afterwards you have to try to model it, and this is what we are trying to do in terms of Lagrangians and field theories, and then putting it on the computer, the bounce actually is non-singular, that you bounce before at high energies before you reach the Planck scale. And what happens then is that, and this is a reasonable, assumption, that it might be the case that gravity doesn't modify first at the Planck scale. We know that we need a quantum theory of gravity to explain a lot of other processes like high energy scattering. So that's out of question. But it might be that space-time itself, just like there are no naked singularities as we believe, it might be that there are no so-called visible Big Bang singularities. It might be this, and this is our proposal really. So we sort of extend the cosmic censorship principle to also imply not just time-like singularities, black holes, but also space-like singularities. And ask the question, is it possible that gravity at very high but below Planckian energies gets modified in a way that enables a bounce that is classical? So you don't crunch. So black holes remain very far apart because they hardly contracted. And so what you see is the blue is how the Hubble patch behaves, how the causal distance or the distance of interaction behave. It shrinks and it grows. So you see here the decelerated expansion phase, then dark energy expansion, then you see the slow contraction phase, and then again bounce and dark energy expansion. However, the physical distances don't follow the same periodicity, but you bounce at a finite value of the scale factor well above the Planck scale. And so this is the proposal, but we are pursuing now, in terms also of writing down the physical theories, the modifications of the gravity. And this is really the picture how it would look like, that it's an evolution which is truly cyclic. It's a universe that has, strictly speaking, no beginning, but undergoes periods of slow contraction, classical crunchless bounce and expansion. And let me just close with the entropy problem that I was emphasizing all the way through. So one part of the entropy problem is certainly alleviated. And this is very similar as to what Penrose is proposing, except he doesn't have an underlying field theory for it. In this conformal cyclic cosmology, if you don't undergo, so slow contraction naturally relaxes all gravitational degrees of freedom. That's why if we measured anytime soon primordial gravitational waves, it would be a theory that's ruled out. So it naturally freezes out all gravitational degrees of freedom, naturally homogenizes and isotropizes the matter radiation sector, and stores all the entropy in the scalar field sector, which it says homogenize and isotropize itself. And during or before the bounce, this is the process that we call reheating, very similar as to what in inflation is called reheating. This very uniform matter radiation, scalar field energy density now decays and transmits into the matter radiation sector, which now for this reason creates it also has a low entropy because it's also very uniformly distributed without affecting gravitational degrees of freedom. So the partition problem of the entropy is definitely alleviated if you have a crunchless bounce. Now you might ask it, and I know that I will get this question, and I have to say I really don't know. I won't solve the problem of the arrow of time. I don't know. I had no comment to it, so I don't know why we at all ever starts more. But what I can tell you is that what's happening is with the entropy versus entropy density. So if you ask is, do I violate at any point the second law? Because it looks like that, I'm shrinking. Isn't the entropy total? And how can I not shrink the entropy or shrink the entropy to the bounds, and nevertheless the second law is not violated? Then one thought here is that we do measure the entropy over all of space, right? So we measure the entropy, overall entropy grows. So if you take the initial patch that then starts to contract, and you take the entropy that was in the initial patch, no matter how big, that will be growing. What's happening is the entropy density in your Hubble patch that is shrinking in on your patch is shrinking because the Hubble patches, Hubble radius is shrinking in so fast on your physical distance. So what this picture decouples is, and it's not I don't consider it as a final answer to the actual thermodynamical entropy problem. I think it shows you a way why it's not an immediate contradiction with cycling, that by the overall entropy grows, the entropy density that is accessible to you during slow contraction is becoming less and less. So if your initial worry was, and you might tell me it's not, but your initial worry was why the entropy density is small at the onset of decelerating expansion, then this picture would give an answer. If your question is where is all the entropy comes from and what is the initial entropy, and I believe that many of you probably associated with that, with the arrow of time, I cannot tell you that. I don't think that we have an answer to that. The only thing what we have an answer for is that it's flowing in one direction, because at each bounce, more entropy gets generated, and during each decelerated expansion, more entropy gets generated. And so what shrinks is the entropy density, but entropy is always growing. This is where I stop. Thank you.
Thank you very much. So, okay. Can people tell me,
if I leave the microphone on here, is that causing a problem for people, or is it okay? Okay, hearing no objections. Thank you, Anna, that was great. So I had a bunch of questions, but then you went on to kind of answer a number of them as we went, but I might ask you to answer them again just to make sure I'm thinking.
Please.
But usually we ask the people in Geneva, I guess usually because they're the only ones who are on Zoom, to go first, but maybe we'll stick with that anyway. Chris, or any of your group there, do you have some questions?
So I certainly have a number of questions. I see that we don't have all that much time. Maybe I just ask the most burning question to start with, and then we see how things.
And by the way, let me say, people can either sort of raise their hands, virtually, using the reactions, or they can put messages in the chat, and I'll keep an eye on I'll keep a list.
So one obvious question I have is whether there's any empirical signature of, say, the new cyclic universe of your model compared to the inflationary models. I know that this is a very difficult question because they have many parameters, really many different models. And I think you probably have as well, at least to some degree. But nevertheless, it would be very interesting to see whether there's any empirical signatures in the cosmic microwave background, for instance, or something like this.
Good.
And whether
should I go? Okay, sorry. I can. This is
in particular, whether you can also get the Gaussianity that you get, as I understand it, from inflationary models.
Yeah. So this is a great question. So, look, I think it would require probably a separate discussion how to distinguish things from inflation, because at this point we know that whatever gets measured is compatible with, there are zillions of models. So let me not get into that, but let me just, it's perhaps more interesting. What would we have to see in order to know that we are wrong? I know that in some sense it's a really old Popperian attitude, but to a certain degree, I believe it's necessary that in science we can say when we are wrong. The theory is, you can debate with me, but I think that we should not be able to be compatible with all possible experiments, whether it's technologically possible to carry them out or not. And this is very simple, that we will know within 5 to 10 years if we are wrong. Because, so I was hinting at it that during this phase of slow contraction, what you need is really to freeze out, to not to store any excitations in the gravitational sector. And what's happening is that during slow contraction, there are 3 features that you might see in the microwave background, and 2 of them you cannot. during slow contraction, what slow contraction would produce. And the three features are, what are the excitations that you could measure? Scalar, energy density, that translates to temperature, you have to see that. Vector, you should not see that because then your universe is not homogeneous and isotropic, so any smoothing mechanism will exclude them. And we don't measure them indeed in the temperature spectrum, so that would have some directionality to the temperature spectrum. And there's a third, gravitational waves. So there are different types of gravitational waves. There are gravitational waves that are generated. So these are really truly excitations of the metric degrees of free tensor, metric degrees of freedom of spacetime. They can be generated to super energetic events like the collision of two black holes or two neutron stars. Those are events that one measures nowadays, tries to measure with LIGO, and then later hopefully we'll measure them with LISA and other grand-based experiments. But there are other type of gravitational waves when space-time itself can be excited through the overall space-time dynamics. And if it's a very high energetic event, like the old models of inflation would have predicted, then due to the super high energy event, gravitational wave would be excited. That's what Penrose says. This is a problem for the initial entropy. Now, of course, nowadays we know how to design models in inflation that don't excite those modes, but in the slow contraction model, there is no way to excite those modes. So in inflation, you have a continuum. You can the amplitude of the gravitational waves. There are a lot of experiments right now going on from Simon's Observatory to LIGO to CMBS4. So within the next 2 to 10 years, we will, and BICEP 2, I'm sure many of you have heard of, that was the initial effort where they thought actually they reported it. So you can have what they measure is the ratio between the amplitude of temperature fluctuation, amplitude of gravitational wave fluctuation, as people call the tensor to scalar ratio. Tensors are the gravitational waves. And inflation can predict from order 1. That would be compatible to it to 0, essentially, depending on how you design your model. And in the slowly contracting phase, there is nothing to excite the gravitational wave degrees of freedom. So we know that we cannot measure anything where the tensor to scalar ratio is about 10 to minus 6. So in the next few years, it will be pushed down to 10 to minus 3. And so if BICEP 2 had been correct, then this theory would already be wrong. And it's really, really not possible to design even arcane models that do this and predict the Gaussian spectrum. So because what you would need is really some gauge fields. Some people do this. So some really complicated, ugly structures, violent modifications of gravity at low energies that we have no sign of. So, if you are not willing to do all the kitchen sink models that, some people will always be willing to do, I think that if you rely on Einstein gravity with canonical scale, even if it's multiple scalars, even if it's, mild modification, even if it turns out that you have to modify Einstein gravity, just not. And the simple reason is because this very rapidly shrinking negative Hubble parameter or rapidly shrinking Hubble radius blue shifts everything. And it blue shifts everything quicker than the perturbations. So the perturbations are also blue shifts, everything grows, but the background energy density just overwhelms everything, including quantum fluctuations. And that's why you can just not have a measurable signal, density fluctuation signal, or gravitational wave signal. Now, second question, and that's now easier to answer also. Now you might ask, didn't you, got rid of the baby with the bathwater, because now you tell me you cannot have density fluctuations. And that's true. So we believe that so the density fluctuations have a whole story. It's good to get them, but in inflation, they lead to eternal inflation, and we cannot directly get them. So what we get is we get isocurve, so relative density fluctuations. They are the only degrees of freedom. So you have multiple degrees of freedom, for example, 2 scalars, so scalar and radiation. So there are different types of models. And what you can do is those fluctuations can redshift instead of blue shifting, because they don't feel the background. They feel the relative. So that you can easily imagine that there are two types of energy densities. Let's say 2 scalars that fluctuates relative to one another, and those fluctuations, it can be calculated, indeed produce a simple spectrum. And then what happens is during the bounce, and there were such models of inflation too, they are just not very natural. That it was called curvaton models. They cannot do anything but convert into density fluctuations. Now, you can say it, I often mention it, it's on the one hand, it is, if you can't have any scalars, a complication, it's a slight complication. On the other hand, you still have very clear predictions about the gravitational wave spectrum. And so I would love to see this being simplified, if you ask me. It's right now a matter of principle argument that it works, and we don't produce this eternal inflation, eternal contraction effect, which personally I'm bothered by. That's many colleagues are not bothered by. So the question is that we can do it, but if you ask me if it's as as pretty or as robust or as I would say definite as the background and the fluctuation, I would say no. So I mean, it's in full honesty, I would say that is something one has to work on. It is right now a matter of principle argument. There is no roadblock to do it. And then the spectrum turns out to be Gaussian if you do it. But this is a little bit more like an inflation. You could have gotten it was a non-Gaussian. So the density fluctuations are just like in that's why the tensors are more important in my view. We don't have a definite spectrum. This is just as kludgy as an inflation. We just know that we can make quantum fluctuations in the relative energy density is redshift, give an L scale invariant spectrum, which is nearly Gaussian, and then transforms into density fluctuations through the bands. But there is nothing that tells into the theory, just like an inflation, why it should be Gaussian, cannot be non-Gaussian. So I would say that that's something I think cosmology we know how to do, but we don't know why it goes the way it goes. We certainly, and I think that's something that I would like to see it much improved. I don't have right now a great idea. I'm right now working more on the bounds and on the back on the simulations, but I would love to see some colleague coming up with some great idea, whether it's in the context of inflation or contraction, that makes it more predictive.
Excellent. Thank you very much.
Thank you. Anyone in here?
I saw a question in the chat, so I am happy to answer that.
Yeah, why don't you go for that, Vitaly? Do you want?
Yeah.
Are you there, Vitaly? Do you want to say the question, or should one of us read it out?
Yes. Hello. Thank you very much for your talk. Yes, I can repeat my question like verbally. So I mean that the cyclic universe models you are developing do not require extra dimensions or the string theory, while those models like extra dimensions and string theory derivatives various, they have predictions for probabilities of rare processes, which we are searching at accelerators, like rare decays, for example. Does it mean that cyclic universe model doesn't have any predictions or predicts the absence of rare processes? Or do you have, or your model, does it have own predictions for rare processes? Are there any publications on this or probabilities published? Or
okay, so it's a lot of great questions at once. So let me just pen back and I'm sure that you and others in the audience know it, but the original Steinhardt-Turak model was very much motivated by string theory and brains and extra dimensions. And so I'm not working on that. They were also implying that when the brains collide, that's when you bounce, and it's a singular bounce. And, I'm more of a just simple cosmologist in the sense that, so there are two, and I will get back to in what sense we consider string theory or may be compatible with it. That, this is a 3+1 dimensional model, and it really is concerned with the background evolution and how to generate fluctuations and how to transmit to the bands by, looking at the gravitational sector and the simple scalar field models with canonical kinetic energy and negative potential and what might be. Now, though nevertheless, so in that sense, we don't need string theory as the early models needed. That's actually an intention. But there is a big program, mostly promoted by many people, Kumron Waffa at Harvard, Robert Brandenburger, and others who ask, what kind of effective field theory should one be allowed to consider? So in this sense, I'm only looking at the effective theory part, low energy effective part, at least low energy relative to string or quantum gravity, that might be compatible with some consistent theory of quantum gravity. And there's some people call it the swampland program. And in that sense, that actually is, and it's a full other talk, and I'm not working on it, but they say that it's actually not so easy to get within those programs inflation. Because there are certain conditions, and this has nothing to do with what particles we produce. So in that sense, whatever comes out as the right theory of quantum gravity, I trust they will explain that. In that sense, I don't have, as you would say, distinct predictions for that. But what I'm concerned with is, can I be compatible as an effective theory are the theories that I'm using, for example, for slow contraction and perhaps even for the bands, good effective theories that may or may not come from some consistent finite theory of quantum gravity. And it looks like, and that's, it's really something what Robert has been Brennenberger writing about lately a lot. It looks like that it's easy to get in, and Qumran says the same thing in within their considerations, negative potential. So let's say string theory is full of ADS type of vacuum, and a negative exponential potential is like an ADS. We just come out of it. So they would say that the scale, at least for the slow contraction phase, what we are using is compatible with string theory. And the other aspect of it is actually, I'm writing right now a paper with one of my master's students that we exactly go through it, what type of potentials we would need and how it can be perhaps compatible with Swampland criteria. Like the scalar field doesn't roll too much. It's steep, it's negative, it's not flat, and positive seems to be difficult. That's what inflation requires. So this is the extent I care. Of course, there's a second part that, I don't know the answer to right now. We are looking at also modifications, low energy high energy, low energy, in the sense that, the modifications of gravity that we introduce are at very high energies, but still not, at quantum gravity energies. And then you might worry, well, what theories can you look at that don't need many quantum corrections to be that are within the regime of their validity? And so what I'm looking at is either type of theory that some Galileans or Hornetsky theories that by some measures looks like that they don't require, that they are good effective theories. Now it's an open question if they can be coming from string theory. But in the terms of low energy effective field theories, it looks like that they are symmetry protected by this Galilean symmetry protected against quantum corrections. I'm sorry if the answer is too technical, but I just want to. So these are the thing. This is the thing that goes into what I'm doing, and I'm not doing string inspired models. And the best person who does this, two people. Robert Brennenberger is definitely the person who has been promoting, S-brane balances, string balances for a very long time. So he has a lot of papers on it in what sense it, and he keeps working on it actively. I'm sorry. and the other person is, of course, the string gas cosmology of Waffa. So those are the people who really ask the question, could you balance? Stefan Alexander works on, Chern-Simons terms induced balances. So there are people who work on it. I'm not working in that sense on how we can fit this into string theory or not.
Thank you very much.
Thanks for the question.
Sure. Hi. So you sort of got into this near the very end of the talk, and you sort of waved it away. But I want to bring up this entropy issue. The way I'm going to bring it up, though, is to hear more about how we're supposed to physically think about the Hubble interaction scale, or the Hubble radius. And so in like classic sort of lambda CDM cosmology, there's a very natural physical reason why we would be taking that as our unit. And I wonder, is there any sort of natural reason we would take that as our unit in, say, the cyclic model, or even just a single smooth bounce model? And the reason why I'm asking it that way is because it seems like if there is a reason, if there is a good physical reason to take that as the unit, then that might have implications for how we think about either entropy or entropy density as the relevant quantity.
So I always bring these two notions together, but the reason is there are two types of horizon that cosmologists love to define. One is the event horizon, the other one is the particle horizon. And if you decelerate, so it's already in inflation, it's a different horizon that you, I think it's in fast contraction decel, but I might confuse, which is I know that during decelerated expansion, the Hubble radius, Hubble patch is the particle horizon. And the event horizon is bigger. So that's what you look at. During accelerated expansion, inflation, slow contraction, you look at the event horizon and you get the same. So it's tricky. So let me say it's why it's tricky what is the Hubble patch approximately, whether it's equivalent to the event or the particle horizon. It's because exactly of this relative scaling or relative dynamics of the scale factor and the Hubble parameter. When the Hubble radius is expanding faster or contracting slower than the scale factor contracts or expands, then your particle horizon is the one that gives you the rate of causal interaction. So you can write an integral over CDT, right? And where it's conformal time, and then you get that is equivalent either to particle or event horizon, and then you get which one at which stage is the Hubble parameter or the Hubble radius proportional. So that's how the calculation goes. But it always goes back to taking an integral over how far you can see, how far light can, maximal distance at which light can propagate at a given time or between given time intervals. So that's always so I probably should have started. I'm sorry to think loudly, that we always take the same integral at some point, and it's always corresponding to one of the two horizons, which then the Hubble radius corresponds to. But it always measures. So the real motivation is what I said in simple things. It's always the distance as far how we can see, and we think, as far we can see tells us what is the maximum distance at which interactions are possible. So that's the physical motivation for it. It's really the scale of, coming from the fact that gravity is local, what is the maximum distance as to how far we can see. And that's usually some order of one parameter times the Hubble radius. And then sometimes it corresponds to your particle horizon, sometimes your event horizon. And I even know since you asked it, you probably know it, where it's beautifully described. Is Mukhanov Physical Cosmology book, has a very accessible, I think it's either the first or the second chapter on horizons, how you define it, how they relate to the Hubble horizon. So I'm on top of the head, will not be able to do it, but send me an email and then I give you the calculation. But the idea is really always this: define the maximum distance of causal interactions.
Thank you.
Sorry.
Yeah, can I just ask thanks for the talk. Can I just ask a clarification question? You mentioned like the cosmological entropy at some point, and then you said it's not the thermodynamic entropy, and I was just wondering, could you, maybe I missed your explanation, but could you say a bit more how they're related? And when you say near the end that, the second law is obeyed, are you talking about the second law for the thermodynamic entropy, or some kind of analogous law for the cosmological entropy, or maybe they're the same thing? Yeah. Could I just hear a bit more? Yeah.
I guess it's very often it's just like with the Big Bang or Big Bang cosmology. Very often, a terminology gets adapted that has nothing to do with some other use of the terminology. So what Penrose calls entropy, I think most people would not consider necessarily related to any type of entropy. Some mathematicians, for example, Elliott Leib, who spent his life working on statistical mechanics, would say he cannot even define gravitational entropy. Sorry, it's in the sense entropy that very often relate entropy with counting certain degrees of freedom, and that being excited, or the number of ways they can be excited, measuring entropy. This is really a pedestrian definition. And in this sense, gravitational entropy, this is, I think, the simplest way. And, Penrose gives numbers to it and relates it, for example, to vacuum energy. But how he would describe it as really the number of gravitation, so the degrees of freedom that are excited in the metric sector. So are the gravitational wave degrees of freedom, the vector degrees of freedom, or the scalar degrees of curvature, scalar curvature degrees of freedom excited? And I don't think that we have a sharp definition of it, as opposed to, the very well worked out statistical mechanics definition of entropy starting, worked out already by Boltzmann. And then today it's been further refined. So in this sense, it's probably an unfortunate nomenclature to call it entropy, but I don't think that there is more relation to it that I can give you than just, a certain, the measure by how much the certain gravitational degrees of freedom are excited. And, the thermodynamic, in a sloppy way, of course, there is a much more sophisticated definition of it. We can think of that as a thermodynamic entropy too, with respect to thermodynamics. But of course, in statistical mechanics, it's underpinning that notion that's much more carefully worked out. And I didn't really wave it off. I just like to say that I'm not an expert, because, this is really something that I didn't, do much work on or do any work on. and therefore, I'm not the best person to ask about, arrow of time, more about thermodynamic entropy than, just adiabatic versus non-adiabatic processes. So I just feel like, I'm not competent enough to comment on it intelligently. That's everything what I wanted to say.
Well, that answer notwithstanding, since you are the most competent person to talk about this model in the room, I'm kind of going to ask you about it anyway. And if that's the answer. So, kind of a couple of things. Maybe you will feel competent about this. So the first question is sort of whether, am I still right that the physics that you're putting in here it's just GR, so it is supposed to be time symmetric?
Modulo the bounds. Well, yeah, the gravitational part, yes, but not when I was swallowing it a little bit. Of course, when you transform the scalar field energy density it decays into matter and radiation, you create a lot of entropy. So in that sense, the cosmology is not time reversible. The gravitational laws might be, but you have produced entropy, so you cannot completely reverse the process. So what you generate is thermodynamic. Yes.
So, I guess the way you think about it in just sort of simple cases of thermodynamics, you'd have the time asymmetric thermodynamical laws, but then you'd say, well, the puzzle is we have some fundamental laws governing the collisions of particles or whatever it is that are fundamentally time symmetric. So in your models, are the fundamental laws time symmetric? I guess that's the question. Yeah.
Yeah, except for, okay. So I don't have any, it's not less or more time symmetric than the other laws, that we describe, let's say lambda CDM by. So I don't add anything more to it. So the only thing what I know is that there are non-adiabatic processes, but they don't have to do anything with gravity. So you ask, is the gravitational law that I'm applying is time symmetric? So that's definitely is. But I don't think that we have discovered any, GR is time symmetric, right? So the problems are not worse or less or better than with GR, because so perhaps it helps. Everything is covariant. So even when that is one of the lead principle of how I'm trying to model the bounds, that the underlying theory is covariant. So it's a very vanilla modification of GR. So it doesn't add anything to that discussion. And for that reason, it's time symmetric. And the only thing what you can measure is, this more pedestrian notion of what happens with entropy density and so on. But there is no, from the gravitational sector, there is no time asymmetry coming in.
And is there matter that behaves in a time asymmetric way? I guess since you put it that way.
Yeah, it decays, right? Usually when you generate entropy, that's very similar. That's why I'm saying that is the least innovative part of the model, since that's already what people imagine in inflation. After, at least when inflation locally stops, that scalar field has to decay into the particles of the standard model and dark matter, and that's when entropy is being thermodynamic entropy is being generated. So that's what one calls reheating, and one hasn't really made much progress with. I would say with really working out the details of that process in the context of inflation or in our context. So that these are open questions. That's why I'm saying that in the sense I don't feel competent, that I haven't worked on this particular issue, and we haven't added to that particular issue. So I think that cosmology hasn't added to it, no matter, there are some people who claim otherwise, but, in a stringent way that's empirically anyway accessible or testable, we haven't added to the question. I think this is fair to say, whether us or inflationary cosmology, any other type of cosmology.
But even the inflationary asymmetry, we think, surely one thinks sort of, that asymmetry arises because of an initial condition, even though the physics that's, it's quantum mechanics, it's time reversible unitary quantum mechanics that's actually driving it. And so the asymmetry isn't attributable to the laws, it would be attributable to the initial condition. So that's still the situation here.
Yeah, that's what I meant, that we didn't add to that anything when I said that, I cannot explain the arrow of time. This is just something, or the initial, that's exactly that is in,
Okay.
I don't know. If you ask my opinion, I don't know if we can make progress on that much, but that's because it probably would require changing the laws, but I don't know.
Okay, so in particular, if I ask the question, well, why aren't we at equilibrium, or why aren't, given that we're not at equilibrium, why aren't we, in both time directions at a local minimum of the entropy? That's the kind of question you don't have an answer for. Is that right?
I mean, at some point, yeah. So if the answer would be that I would have to explain why the universe has never been in equilibrium, then I don't have an answer to. And just like with any other, as you say, it's an initial condition assumption. In order to do cosmology, I have to assume wherever I start, it won't be equilibrium. Otherwise, we would still be there. But this is, we just don't, I don't think that there is any progress being made really that is generally accepted. And I certainly cannot add to this discussion. I just try to be honest about it, that, we haven't added to it.
Yeah, no, I think that's both helpful to see what's going on, and also kind of how a cosmologist thinks about that question, which is pretty interesting. Okay. Well, we're kind of out of time unless somebody has a
I'm happy to answer email questions if there is anything. So please don't feel that it's like completely cut off. And if something comes up, just email me. I'm good at answering email within just 1 or 2 days at most.
Lucy has a question in the chat.
Oh, okay.
Yeah.
So I thought it might be related to a previous question. So I kind of asked it as you were talking about something else to do with the relationship between gravitational and thermodynamic entropy.
Yeah.
But I was wondering about the infinite entropy that crops up in the Big Bang, Big Crunch picture. Just kind of some intuitions for how to think about what infinite entropy means.
Good. So it's more like that. It's a great question because you point out the feature of the model. So the point is that you might ask in general if the cycling can be infinite or finite, and what does it take for it to repeat infinitely often? Well, it can technically, because it's conformal. So the fact that I mean the gravitational evolution is so that the scale factor never goes to 0, therefore you can reset. The scale factor doesn't have any meaning, its value. So you can infinitely often reset it, or nothing has it, cannot repeat infinitely, except for one feature. If space is not infinite. So if you have a finite, if you insist that it has to be finite, that's why your question is great. Then it cannot go infinite. Then it has to be finite, and then the total entropy has to be finite too. If it turns out that there can be, an infinite space, and I don't know if there is any reason why not to assume that, then probably the total entropy could be infinite, and maybe that could be, but then you would have to have an answer, why does it still have a direction, or the entropy density locally why it goes, but it really comes down to it, these are the more philosophical assumptions that I'm not so intelligent to talk about, because I never thought about it, what speaks against infinite space-time versus finite. Infinite space versus finite. It's really just space, it has to be finite versus not. And if it's finite, then you usually are back to the problem that Nick was presenting, that at some point you have to assume that you start with a non-equilibrium low entropy, and then from there on you can keep going. If it's infinite, it's probably just a different option, and then you have a different entropy question. So I don't know the answer to it, but I just wanted to point out that you pointed out a very important distinction that we have to make in this model. So thank you.
Okay, so it's about 1 o'clock, so we should, let's say thank you one more time for this great
and
talk.
Thanks for enabling
great
the Zoom. I'm really glad that I could give the talk this way. Thank you. Nice meeting you. Thank you.